Today I'm going to model a few different multiplication strategies that we have talked about in class and show some examples of them. And you can use this as a reference for yourself if you need help figuring these out, or if you just want to see some more examples of the different strategies. So the first one is a partitioning or decomposing strategy. So this is any time that we break the numbers apart in any way to make the math easier for us, or to do the multiplication. So the first one is 27 times 4. So to do 27 times 4, I'm going to decompose the 27 into 20 and 7. So I'm going to do 20 groups of 4, which is 80. And I'm going to do 7 groups of 4, which is 28. So together that will give me 108. And I know that works because I needed 27 groups of 4, and I have 20 groups and 7 groups. The next one, 32 times 12. The easiest way to decompose this one, that most students would see, would be to break up the 12 into 10 and 2. So we have 32 times 10 equals 320. And we have 32 times 2, which is 64. And add them together, we get 384. That'd be the simplest way to decompose that number. But another way that we could think about it, erase some of this here. Another way some students might think about this would be that 12 is 6 plus 6, or double 6. So really you could do 30 times 6 and 2 times 6. So we have 180 plus 12, which is 192. But because we have 2 groups of 6 and 12, we would then have to do 192 plus 192, which would give us 384, just like the other way. One more problem we could do with a decomposing strategy is 22 times 9. And the way I would think about this one would be 20 times 9, which is 180, and 2 times 9, which is 18. So I get 198. Another cool way you could think about this would be to divide the 9 into 3, 3 and 3. So we need 22 groups of 3, but we need it 3 times. 22 times 3 is a pretty easy problem to work out and to kind of think about. So it's 66, and then we would just do 66 3 times. So 6 plus 6 plus 6 is 18. Carry my 10. 60, 60, 60 is 180, plus 1 is 190. The next strategy is one that is not as straightforward for some people, for some students, or even for me. Sometimes it doesn't make quite as much sense as the decomposing one. So let's look at that same problem from before, 22 times 9. So we could do this one with a compensation strategy, where we think about the 9 as a 10. So instead of doing 22 groups of 9, we're going to do 22 groups of 10, because 10 is a nice number, friendly number. So we have 220. But then because we added one more group of 22 here, we need to take away that same group of 22 from our answer. So we're going to have 198, like we did before. Another one that we can do that with is 29 times 6. So this time, the 29 is really close to 30. So I could think about this problem as 30 times 6. So 30 times 6 is 180. But then I added an extra group of 6. So I need to take that group of 6 away. So that leaves me with 174 for 29 times 6. Another compensation strategy that some problems might lend themselves to, or that some students might see, is where you half one of the numbers and double the other number. So you manipulate the problem that you're working on. So instead of 220 groups of 5, we're going to think about that as 110 groups of 10. Because we can half the 220 and double the 5, and we're still going to get the same answer. So 110 times 10 is 1,110. 1,100. That's not a very common compensation strategy, and it really would only lend itself to certain problems, especially if you have where you're multiplying by a 5 and you have a larger number on the other side. Doubling the 5 to a 10 sometimes makes a lot of sense and can help the problem. So for the ever popular lattice multiplication, which seems to be becoming more popular in certain curriculums, elementary curriculums, is lattice multiplication. So it's kind of like an array, but not quite as place value friendly. So I'm going to try to do this in colors so you can kind of start to see where the place value is, but also just remind you of the strategy. So anytime you have lattice multiplication, you create a rectangle and you put the numbers on the top and down the right hand side. And the key is that however many place values you have in your first number that you're multiplying, that's how many columns you have. And the number of place values in your second number, that's how many rows that you have. So because I'm doing a 2-digit by a 1-digit, my rectangle is 2 by 1. So I have 72 times 6, and I'm going to draw my diagonals here so we can keep track of the place value. And what those diagonals do is it does make a row of the place values, and we'll see that with the colors that we're going to do here. So the first number is 2 times 6, and we know they're both 1s, so it really is 2 times 6, which is 12. So I'm going to put the 2 on the bottom and the 1 on the top. And I'm going to make the 1 blue because it is actually a 10, because it's a 12, so it's 10 plus 2. And now I'm going to come over here to my 7, and I'm going to think 7 times 6 or 70 times 6, either way. If I do 7 times 6, I get 42. And really, in our heads, we know that 70 times 6 would be 420. So the 2 in that number is actually a 10, because it's 420. And then the 4 is a 100. So it's... Now, for the lattice, we just add down the diagonals. So the first diagonal I have is my 1s column. So all I have here is a 2. In my 10s diagonal, I have 2 10s plus 1 10. So that gives me 30, or 3 10s. And then the last one, I have 4, which is 4 100s. So my answer is 432. Another lattice multiplication problem here is 56 times 43. So you can see, because I have a 2-digit by a 2-digit, my array is 2 by 2 with all my numbers in the right places. And again, I'm going to kind of color code this so you can see where all the place values are. And I'm going to start with the 6 times the 3 because it's my smallest place value. So I know that 6 times 3 is 18. So in that number, the 1 is a 10 and the 8 is a 1. So I have 18. And if I come down here, I can do 6 times 40, 6 times 4. And so in that number, 6 times 4 is 24. And because it's really 240, my 4 is a 10, and my 2 is a 100. 240, 60 times 4 is 240. I'm going to come over here, and I'm going to do 3 times 50 next. So 3 times 50 is 15, or 150. 15 tens, or 150. So if I have 15 tens, I have 15, and the 1 in that number is in the hundreds, and the 5 in that number is in the tens. And last but not least, I have 50 times 30, or 5 times 3, and I know that 50 times 30 is 1500, but I'm only looking at the 15 part for my lattice, the 1 and the 5, so I can see that the 5 is in the hundreds place, and the 1 is in the thousands place. So now I add down my diagonals. I have 8 ones. I have 5, 6, 7, 8, 9, 10 tens. So I'm going to put the 0 here for the tens, and then I have that extra that comes up here to my hundreds column. And in my hundreds, I have 500, 600, 700, 800, 900. And in my thousands, I just have 1,000. So 56 times 43 is 1,908. 1,908. So let's do one more lattice multiplication, and this time I'm not going to focus on the place value. If you want to try to figure that out as we go along, think about where the colors are and what you're actually multiplying when you make these boxes. So I'm doing a 3-digit by 2-digit. 208 goes on top, and 26 goes on the right. Make my diagonal lines. And again, just remember, these are my ones, these are my tens, these are my hundreds, these are my thousands, and these are my 10,000s if we need it, which we will in this problem. So I'm going to start with 8 times 6, which is 48. I'm going to do 8 times 2, which is 16. 0 times 2 is just 0, so I'm going to actually just leave it blank. 0 times 6 is also 0. 2 times 2 is 4. And 2 times 6 is 12. So now I add through my diagonals. I have 8 ones. I have 6, 7, 8, 9, 10 tens. So with 10 tens, I actually will have 100. Move that up there. So now I do my 100. So I have 1, 2, 3, 4 hundreds. And now I have 4 5,000s. So my answer for 208 times 26 is 5,400. 408.